Welcome back to the deep dive. Today we are doing some pretty heavy lifting.
We are.
We're looking at a piece of technology that is, and I don't think this is an exaggeration, quite literally the foundation of the modern world. Yet it is almost entirely invisible to the billions of people who use it every single day.
That's the fascinating part, isn't it? The most critical infrastructure is the stuff you never see.
Exactly. We're talking about the internet's address book. Or, to be a bit more precise, we're talking about the crisis that threatened to completely break that address book.
A crisis decades in the making.
And the massive, incredibly complex, and frankly, elegant engineering solution that is currently fixing it. We are talking about the transition from IPv4 to IPv6.
I've heard it described as rebuilding an airplane while you are actively flying it across the Atlantic.
That feels about right.
It's fundamental, it's inevitable, and it's happening right now, packet by packet, under our fingertips as we're having this conversation.
And I think most of our listeners, they've heard the term IP address. It's that string of numbers you see when you're troubleshooting your Wi-Fi router, or you get that error message. But the scale of what is happening here is, well, it's difficult to overstate.
It really is.
We aren't just getting a simple upgrade. We're moving from a finite, scarcity-based system to a system that is, for all practical human purposes, mathematically infinite.
You've hit on the key philosophical change right there. We're moving from a scarcity mindset to an abundance mindset.
Abundance, that's a great way to put it.
And that shift, it changes more than just the number of devices we can have. It fundamentally changes the architecture of how those devices speak to one another.
So let's start at the beginning, the problem, the address crisis. I was looking at the history here, and it all goes back to the very beginning. ARPANET.
Right. Back when the internet was basically a research project for universities and the military in the late 60s, early 70s.
And when Vint Cerf and the other early architects designed the addressing system, what we now call IPv4, they used a 32-bit address space.
Right. And to be completely fair to them, in 1981, when the standard was finalized, a 32-bit address space seemed like absolute overkill.
It must have seemed astronomical.
Totally. 32 bits gives you roughly 4.3 billion unique addresses. You have to remember, at the time, computers were mainframes the size of entire rooms.
Right.
The idea that we would ever need to connect 4.3 billion of them was, well, it was laughable. That number was larger than the entire human population of the planet at the time.
But then reality and Moore's Law caught up fast.
It did.
The internet goes commercial in the 90s. Then we all get mobile phones. Then we get always-on broadband internet. And suddenly that bucket of 4.3 billion addresses starts to look like a tiny puddle in a very big drought.
Exactly. We hit the wall. The Internet Assigned Numbers Authority, or IANing, the top-level organization, they officially handed out the last big blocks of IPv4 addresses in 2011.
2011, so over a decade ago.
Yep. And then in North America, the Regional Registry, ARIN, they ran out completely in 2015. We have been running on fumes and clever workarounds for years.
And I want to touch on those workarounds. We've basically survived this exhaustion using some clever hacks, right? Primarily a thing called NAT.
Network Address Translation, yes.
That's the thing where my router gets one single public IP address from my ISP, and then all my devices, my laptop, my phone, my smart fridge, my watch, they all hide behind it using these fake private addresses.
Fake is a harsh word, but it's functionally accurate.
Yeah.
What NAT did was it broke the original end-to-end principle of the internet. The whole original design was that any computer on the network could talk directly to any other computer.
A true peer-to-peer network.
Exactly. NAT put up a barrier. It forced our devices to hide. IPv6 isn't just about getting more numbers so we can keep hiding more things. It's about restoring that original end-to-end connectivity.
So my smart fridge can be a first-class citizen on the internet again.
It allows every device to have its own unique, public, reachable identity again. No more hiding.
So let's talk about the scale of the solution, because this is what gets me. IPv4 is 2 to the power of 32. IPv6 is 2 to the power of 128.
It's a number that's hard to get your head around.
I've seen the analogy that if IPv4 is a single bucket of sand, IPv6 is all the sand on all the beaches on the entire planet. But looking at the math, even that feels like it's underselling it.
Oh, it definitely undersells it. Massively. 2 to the 128 is 340 undecillion.
Undecillion? I don't even know what that means.
It's 340 followed by 36 zeros. A bucket to a beach that doesn't capture the magnitude. Think of it this way.
Okay.
If you could assign a unique IPv6 address to every single atom on the surface of the Earth.
Every atom.
Every single one. You would still have enough addresses left over to do the exact same thing for 100 more Earth-like planets.
That is a number so large it just breaks human intuition completely. So that begs the question, why? Why go that ridiculously big? Why not just double it to 64 bits? That would have given us 18 quintillion addresses. Surely that would have been enough.
It probably would have been enough for the number of devices, yes.
Yeah.
For the foreseeable future, at least. But the 128-bit size wasn't chosen just for the sheer volume of addresses.
Okay, so what was the other reason?
It was chosen for structural efficiency, for organization. The architects wanted to be able to allocate addresses hierarchically.
What do you mean by that?
To give massive continent-sized blocks to the regional registries, who then give huge blocks to ISPs, who then give enormous blocks to companies, who then give generous blocks to individual homes.
And you can do that without worrying about being wasteful.
Exactly. When you have 340 undecillion of something, you don't have to conserve them anymore. You can organize them. It makes routing on the internet backbone infinitely more efficient. We'll get into that.
Okay, so before we dive into the nuts and bolts of the address itself, I have to ask this trivia question that came up in the research because it's been bothering me.
I think I know where you're going.
We're moving from version 4 to version 6.
Yep.
What happened to version 5? Did we just, skip it because 6 sounded cooler or something?
No, version 5 actually existed. It was a real thing. It was called the Internet Stream Protocol, or ST.
Never heard of it.
Not many people have. It was developed in the late 70s and 80s. It was designed for experimental streaming of voice and video, really early multimedia stuff. It was officially assigned the version number 5 in the IP header.
So it's a reserved number?
It was a reserved number.
Yeah.
It never really took off as a global standard, but because 5 was taken in the history books, the IETF, the engineers who build all the internet standards, they had to jump to version 6 to avoid any ambiguity or confusion.
So IPv5 is the lost, forgotten sibling of the protocol family.
That's a good way to put it.
All right, so let's get into the mission of this deep dive. We want to demystify this 128-bit beast. And I think the very first hurdle for anyone is just reading the thing.
The notation.
The notation. An IPv4 address is friendly, it's approachable, 192.168.1.1. It's decimal. We learned that in kindergarten.
4 numbers separated by dots. Simple.
An IPv6 address looks like a cat walked across your keyboard. It's like 2001.0db8.ac10.fe01, and it just keeps going. It's alphanumeric. It's intimidating.
It is. It's written in hexadecimal. And this is where we really have to leave those sand analogies behind and talk about binary for a second.
Ones and zeros.
Right. In computing, everything is binary. An IPv6 address is a string of 128 ones and zeros. If we wrote that out, it would be completely impossible for a human to read or remember.
It's utterly unusable.
And if we tried to convert it to decimal like we do with IPv4, the numbers would be gigantic, and the conversion logic would be a total nightmare for network engineers to work with.
So we use base 16, hexadecimal.
Correct. And the reason we use hex is because it maps perfectly to the bits. It's a perfect fit.
How so?
One single hexadecimal digit, so 0 through 9, and then A, B, C, D, E, F, represents exactly 4 bits of binary data.
So it's a 4-to-1 mapping.
A perfect 4-to-1 mapping. We call a group of 4 bits a nibble.
A nibble. That's great. It's half a byte.
Exactly. So since an IPv6 address is 128 bits long, if you divide 128 by 4, you get 32.
Right.
That means any IPv6 address is always represented by exactly 32 hexadecimal characters. It aligns perfectly with the underlying math. There's no waste.
So when I see a letter F in an address, what I'm really looking at is 1111 in binary. And when I see a 0, it's 0000.
You've got it. That's the core concept. And to make it even readable for us humans, we group those 32 characters into 8 groups of 4.
And those groups are separated by colons.
Right. We sometimes call them quartets, or more accurately, hextets.
Okay, but even so, 32 characters is a mouthful. If I have to read an IP address over the phone to tech support, we're going to be there all day long.
Oh, yeah.
But the engineers anticipated this, right? They built in some compression rules, some shorthand.
They did. There are 2 golden rules of IPv6 compression that really every network engineer has to master. It's day 1 stuff.
Let's walk through them. Rule number 1. You can drop the leading zeros.
Right. So in any of those hextets, those groups of 4 characters, if you have zeros at the front, you can just remove them.
So if a group is 0056, I can just write 56.
Correct. If the group is 0db8, you can't remove the 0 because it's not at the very front. But if it was 00DB, you could write DB. And if the whole group is 0000, you can shorten it all the way down to a single zero.
Okay, but there's a trap here, right? I've heard this called the checkbook trap.
Yes. It's a good way to think about it. You can only remove leading zeros. You can never, ever remove trailing zeros.
So give me an example.
Think of it like a bank check. If I write you a check for $50, that's $50. I can drop the zero at the front, just write $50. It means the exact same thing.
Okay, makes sense.
But if I drop the zero at the end?
You now have $5. You've changed the value.
Exactly. In hex, 5600 is a totally different numerical value than 56. The position of the characters matters. So rule 1, drop the zeros at the front, never at the back.
Simple enough. Okay, rule number 2. This is the heavy hitter, the double colon.
This is the real magic trick of IPv6 notation.
What's it do?
Because the address space is so incomprehensibly vast, most IPv6 addresses are mostly empty space. Just lots and lots of zeros.
Fields of nothing.
Right. The rules say that if you have a string of one or more consecutive all-zero hextets, you can replace that entire string with just 2 colons.
So if I have an address that's like FE80 and then a whole bunch of zeros and then a 1 at the end, I can just squeeze all of that nothingness out.
Yes.
Ah.
That address would become FE80.1, much cleaner.
That is much, much better. But I'm sensing a catch. There has to be a catch.
The catch is ambiguity. You can only use the double colon once in any given address.
Ah. Okay, why only once?
Well, think about the computer on the other end trying to rebuild the full address. It knows the total length must always be 8 hextets.
Right.
If you write something like 2001.5.1, the computer sees 2 gaps. It has no way of knowing how many groups of zeros belong in the first gap versus the second gap.
Ah.
Does the first gap represent 2 hextets?
Yeah.
3? 4? It's mathematically ambiguous. The computer can't solve the equation.
That makes perfect sense. It's like a simple algebra problem. You can solve for one unknown variable, x. But if you have x and y and no other information, you're stuck.
Precisely. So 1 double colon per address. That's the golden rule.
Yeah.
If you have multiple sections of zeros, you use it on the longest section to get the most compression.
Okay, let's try a practical example. Let's take a long, ugly address. FE80.000000.00000.000100010000123.
Okay, great example. So first, we apply rule 1. We drop all the leading zeros.
So that gives us FE80.0.0.10.0.123.
Better already. Now we apply rule 2. We look for a string of consecutive zeros.
Well, I see a group of 3 zeros right after the FE80 and then another group of 2 zeros after the 100.
Correct. So we have to choose which one to compress. The rule of thumb is to compress the longest string.
So that first group of 3 zeros.
Right. So the final compressed address becomes FE80.100.0.123.
It's still a bit longer than an IPv4 address, but it's manageable. It's something a human can actually work with.
Exactly.
Now, one last piece of notation before we move on to the address types, the slash. In IPv4, we had subnet masks like 255.255.255.0. It was kind of a pain to type.
A huge pain. In IPv6, we have gotten rid of subnet masks entirely. We strictly use what's called CIDR notation.
That's the slash followed by a number.
Right. And the number that you will see 99.9% of the time, especially on local networks, is 64.
64. Why is 64 the magic number?
Because it cuts the 128-bit address exactly in half.
Oh, that's clean.
It's very clean. The first 64 bits are the prefix. That's the network portion. That part of the address tells the routers where you are in the world.
And the other half?
The last 64 bits are the interface ID. That's the host portion. That part identifies your specific machine on that specific network.
So it's a perfectly clean split. The front of the bus is the location. The back of the bus is the passenger.
A perfect analogy. Yeah. And that 64-bit alignment isn't accidental or arbitrary. It was chosen very deliberately to align with 64-bit computer processors and, crucially, to accommodate a standard called EUI64, which we'll definitely discuss later. It simplifies the math for the hardware itself.
All right, so now that we can read the address, let's talk about what the different types of addresses do. In IPv4, everyone is fighting for a public IP address. There's this huge scarcity.
Right.
In IPv6, with 340 undecillion options, how do we even begin to organize the world?
We organize it with a very strict hierarchy. The main category of address you'll see is the Global Unicast Address, or GUA.
So these are the public addresses.
Correct. These are the addresses that are globally unique and writable on the public internet. This is your device's real-world identity.
How can I spot one in the wild? Is there a certain range they fall into?
There is. Right now, INA is allocating addresses that start with the binary prefix 0001.
Okay, and in hexadecimal, 00010 is 2 and 000 is 3.
Exactly. So that means if your address starts with a 2 or a 3, so 2001, 2400, 2600, something like that, that is a live, public, global internet address.
And the distribution of these isn't a free-for-all, right? You mentioned
Right.
a hierarchy. It's a strict chain of command.
It's extremely strict, and this is key to the efficiency of IPv6. At the top, you have IANA. They give a massive block. Let's say a 12 to a regional registry like ARIN, which covers North America.
Okay.
ARIN then chops up that massive block and gives a smaller, but still huge, 32 block to an ISP like Comcast or AT&T.
And then the ISP gives a piece of that to its customer.
Right. The ISP then typically chops up their 32 and gives a 48 block to a business customer.
Hold on. A48. If the standard subnet for a LAN is a 64 and the company gets a 48, that leaves the company with 16 bits of space to play with?
Correct. And 2 to the power of 16 is 65,536.
So you're telling me a single company, just by getting a standard internet connection, has enough address space to create 65,000 separate subnets?
That is the standard allocation.
That is just absurd. In the IPv4 world, a company would fight tooth and nail just to get a handful of public IP addresses. Here they get 65,000 entire networks handed to them by default?
And this is the why behind the whole structure. It's all done for routing efficiency on the internet's backbone.
Explain that. What's root aggregation?
Because of this strict hierarchy, the massive core routers run by the big carriers don't need to know about your little company's network. They don't even need a route for your ISP's network. They just need one single route for ARIN's massive 12 block.
Ah, so it summarizes everything.
It allows for massive route aggregation, which keeps the global routing tables small and fast. It's what allows the internet to scale.
Okay, so that's the public side of things. But what about private networks? In IPv4, we all know the famous ranges like 192.168.x.x or 10.x.x.
Right.
We use those for internal corporate stuff or your home network, things that shouldn't be directly on the internet. Does IPv6 have an equivalent for that?
It does. They are called unique local addresses, or ULA. And you can spot them because they always start with the prefix FD.
FD, got it. Now, in the IPv4 world, those private addresses caused a huge headache known as IP conflicts.
Oh, nightmare.
If Company A uses the 10.1.1.0 network and Company B also uses the 10.1.1.0 network, and then those two companies try to merge.
It is an absolute disaster. You have overlapping address space. You can't connect their networks. You have to manually go through and re-IP every printer, every server, and every single laptop in one of the companies before you can connect the wires.
Which costs millions in IT labor and downtime.
It's a massive, expensive problem.
So how does IPv6, with these ULA addresses, fix this?
It fixes it with probability, pure statistics.
Really?
The rule for generating a unique local address says that after the FD prefix, you must generate a random 40-bit global ID as the next part of the address.
Wait, random? Why random?
Because 40 bits of randomness gives you over 1 trillion possible combinations.
Okay.
The logic is this. If two companies merge, and they both followed the rules and generated their own random 40-bit IDs for their internal networks, the statistical probability of them having chosen the exact same ID is effectively 0.
It's astronomically low.
So you can just plug the two networks together, and they will route between each other perfectly. No conflicts, no redressing.
Yeah. So we basically traded certainty via manual assignment and careful planning for certainty via massive probability.
Exactly. It's the law of large numbers working in our favor. It's a much more scalable solution.
Okay, that's clever.
Now we get to the address type that I think confuses people the most, myself included sometimes, the link local address.
Ah, the unsung hero of IPv6.
If I open my terminal right now on my laptop and type ifconfig, I see an address starting with F80. It's there, even if I unplug my router from the wall. What on earth is this thing?
Link local addresses are mandatory. Every single IPv6-enabled interface on any device must have one.
It's not optional.
Not optional. They all start with FE80. And their scope, their reach, is limited strictly to the link. That is the physical wire or Wi-Fi network you are directly connected to. A router will never forward a packet that is destined for a link local address.
So it's like a shout that can only be heard in the single room I'm standing in. It can't leave the room, let alone the building.
It can't even leave the room. It's the most localized form of communication. But why do we need it? What's the purpose?
Bootstrapping. It solves the classic chicken and egg problem.
How so?
When your computer first wakes up, It has no idea what's going on. It doesn't have a global IP address yet. It doesn't know where the router is. It doesn't know who its neighbors are.
It's completely isolated.
Right. It needs a way to communicate on that local link before it has been configured with a real address. It uses its self-generated FE80 address to do that. It's the language it uses for all the overhead protocols, finding routers, discovering neighbors, exchanging routing tables. It's the foundation everything else is built on.
So the entire infrastructure of the network relies on these local whispers. But there's a really strange quirk here that trips people up. The zone ID.
Ah, yes. The
Yeah.
percentage sign. When you see FE80.1% 00 or something.
Right. What is that percent sign doing in an IP address?
Well, it's because link local addresses are not unique globally. In fact, they're not even unique within your own computer.
What do you mean?
Every device in the world generates an address, starting with FE80. Your laptop might have a Wi-Fi card and an Ethernet card. Both of them will have an address starting with FE80.
Okay, I see the problem.
If you, the user, tell your operating system, I want to ping FE80.1, the OS looks back at you and asks, which one? It's ambiguous. Do you want me to send this ping out of the Wi-Fi card or out of the Ethernet card?
Because the address itself doesn't tell you the location, since they all look the same.
Precisely.
Yeah.
The zone ID, that %0 or %12 at the end, is you explicitly telling the computer which physical port, which interface to use for that traffic. It resolves the ambiguity.
And this leads to something that I found absolutely fascinating in routing tables. If I look at the configuration of a big Cisco router running IPv6, and I look at the next hop, the address of the next router in the chain to get to the internet, it's usually not a global public address.
No, it's almost never the GUA. It's almost always the link local address of the neighboring router.
That seems so counterintuitive. We're trying to send traffic to Google servers, but my router is handing the packet off to an address that starts with FE80.
That's because the routing protocols themselves, things like OSPF and EIGRP, they establish their relationships, their adjacencies, over that local link. It's considered more stable. The global IP of a router interface might change, but the link local address usually stays the same for the life of the device.
So the entire global internet is essentially built on a chain of these local private handoffs from one router to the next?
That's a great way to think about it, yes.
Okay, so this is a good pivot. We've talked about the first half of the address, the network part, the 64 prefix. Now we need to talk about the second half, the interface ID, the last 64 bits that identify my specific machine.
Right.
We can type this in manually, of course, but that's tedious and prone to error. We want automation. And this brings us to a really clever concept called EUI64.
Modified EUI64 to be precise, yes.
Okay.
It stands for Extended Unique Identifier.
And what is it?
It's a very clever way for a device to automatically generate its own unique 64-bit interface ID without needing to ask a server for help.
So it can just figure it out on its own. How does it do that?
It uses the one unique thing the device already has from the day it was made, the MAC address.
The hardware address that's burned into the network card at the factory.
Exactly.
But wait, a MAC address is 48 bits long. We need 64 bits for the interface ID.
Right, we're short 16 bits, so the algorithm does something very simple mechanically. It takes the 48-bit MAC address and splits it right down the middle.
Okay.
It takes the first 24 bits, which is the manufacturer's ID, and the last 24 bits, which is the device's serial number, and it just pushes them apart. Then it inserts a specific 16-bit padding value right in the middle, FFFE.
FFFE. So if my MAC address is, say, 00000.1111111, the algorithm turns it into 0000.111 FFFE 11.1111.
Exactly. It's now 64 bits long. But
There's always a but. There's always a twist.
there is a very specific twist, and this is where we have to go deep into the history of networking standards. The algorithm requires you to take the result and flip the 7th bit of the very first byte.
The 7th bit, why on earth would they do that? That feels like some kind of engineering voodoo.
It does, doesn't it? It
Well-
seems completely random. To understand why, you have to understand the structure of a MAC address itself. The 7th bit in a MAC address has a special name. It's called the Universal Local Bit, or the UL bit.
The UL bit.
In a standard Ethernet MAC address, if that bit is a 0, it means the address is universally administered, meaning it was assigned by the IE to the manufacturer and is guaranteed to be globally unique.
So normally coming from the factory, that bit is a 0.
Correct. But if an administrator manually changes a MAC address, they're supposed to flip that bit to a 1, which signifies that it's now a locally administered address. It's no longer guaranteed to be unique.
Okay, so 0 is universal, 1 is local. Got it. But why did the IPv6 designers decide to flip it?
They inverted the meaning of the bit, essentially. They decided that for IPv6 interface IDs, a 1 would mean universal and a 0 would mean local.
But why? Why change it?
To be honest, the historical reasons are a bit murky, but the prevailing theory is that it was done for convenience for network admins. They wanted the easy, simple addresses like point 1 or point 2 to have that bit set to 0 to signify they were local manual assignments.
So they flipped the logic of a global standard just to make it slightly easier to type short addresses like point 1.
It appears so. So in EUI64, when we take a standard factory AMC address, where that 7th bit is 0, we have to flip it to a 1 to signal this is a universal ID in the new language of IPv6.
That is a deep, deep cut. So for the listener who is maybe studying for a certification exam or just trying to read a packet capture, what does this bit flip look like in practice? Is there a shortcut?
There is a very simple shortcut. Just remember, 0 becomes 2.
Explain that.
The first 2 hex digits of most MC addresses are 00. That's 00000000 here. The 7th bit is the second to last 0 in that string. If you flip it from a 00 to a 1, the binary becomes 00000000.
And 00 and 0 in binary is the number 2 in hexadecimal.
Correct. So if the Manatee address starts with 00, the EUI64 interface ID will start with 02. And conversely, if the MUC address happened to start with 02, the bit flip would turn it back to 00.
So 0 becomes 2 and 2 becomes 0. It's a weird bit flip caused by a design decision made 30 years ago, probably to save a few keystrokes.
I love it. It's the kind of legacy quirk that stays with a protocol forever. It tells a story.
Okay, this is fascinating. Let's move on to how these devices, once they have their addresses, actually find each other on the network. This brings us to segment 5, the death of ARP.
The momentous occasion in networking.
In the IPv4 world, we used ARP, the Address Resolution Protocol. A device would basically shout, "Who has IP 1.2.3.4? Tell me your MEC address." And the way it worked was with a broadcast.
The broadcast. It's the brute force approach. The computer effectively screams at the top of its lungs to every single other device on the network segment.
And every single device on that network has to listen.
That's the core problem with it. It's an interrupt. Every single CPU on the subnet has to stop what it's doing, process that broadcast packet, strip the headers, look at the target IP, realize, oh, that's not for me, and then discard it.
That sounds trivial for one packet, but if you have 1,000 devices on a network,
It becomes an interrupt storm. It's death by 1,000 cuts.
Yeah.
In large, busy networks, your computer can spend a measurable percentage of its CPU cycles just saying, no, not me, to ARP requests that have nothing to do with it. It drains battery on mobile devices. It wastes energy and CPU time across the entire network.
So IPv6 killed the broadcast.
Cold-blooded murder. There are no broadcasts in IPv6. None. Instead, we use something far more elegant, the Neighbor Discovery Protocol, or NDP.
And NDP relies on multicast.
It does. Multicast meaning one to many, but not one to all.
But it's even smarter than just the simple multicast, right? It uses a really clever trick called the solicited node multicast address.
This is where the real genius and efficiency comes from. It's beautiful.
Let's break the mechanics of this down. How does it work?
Okay. When my computer wants to find the MAC address for your IPv6 address, it doesn't shout at everyone. Instead, it calculates a special, very specific multicast address. It's based on the last 24 bits of your IP address.
The last 24 bits.
It takes a fixed multicast prefix, which is FF02.1 FF-AND, and then it appends those last 24 bits of your address to the end of it.
So if my IP address ends in, say, AABBCC, my computer's automatically and quietly listening to a special multicast group address that also ends in AABDCC.
Correct. Your computer automatically joins that multicast group when it boots up.
Okay.
And here is the truly brilliant part. Your network interface card, the NIC, the actual silicon chip itself, calculates this.
It's done in hardware?
It's done in hardware. The NIC programs a hardware-level filter. When that multicast packet, that neighbor solicitation, arrives on the wire, your NIC's hardware checks the destination address. If it's a match for the solicited node address it's listening for, it lets the packet through to the main CPU. If it's not a match, the NIC drops the packet right there.
So the main CPU, it never even wakes up. It's never interrupted.
The CPU sleeps like a baby. The NIC acts as a bouncer at the door, only letting in the messages that are specifically for you. It effectively eliminates the broadcast interrupt storm at the hardware level.
That is absolutely brilliant. It moves the filtering work from the software, the CPU, down to the specialized hardware.
And that's what allows IPv6 networks to scale to tens of thousands of devices on a single network segment without choking on their own administrative traffic.
So that handles finding neighbors, What about finding the gateway, the router?
A very similar process. Router solicitation and router advertisement. We call them RS and RA messages.
Which brings us perfectly to segment 6. How a device actually gets an address in the first place. In the old IPv4 days, we mostly relied on DHCP servers.
We did.
And if that DHCP server went down, nobody on the network could get an IP address. It was a single point of failure.
IPv6 introduces a much more resilient method called SLAC.
That's SLAAC.
Right. It stands for Stateless Address Auto-Configuration.
The plug-and-play dream of networking.
It truly is. When a host device boots up, it sends a router solicitation message to the special All Routers Multicast group, FS02.2. It's basically shouting into the void, "Hello, is anyone in charge here?"
And the router hears that.
Any router on the link will hear it, and it'll reply with a router advertisement, or RA. The RA message essentially says, "I am here, I am a router," and the network prefix for this LAN is 2001.db8.cfe.1164. Go build yourself an address.
So wait, the router doesn't hand out the full address? It doesn't keep a list?
No, that's the stateless part of SLSU.
Yeah.
The router doesn't track who has what address. It just provides the prefix. It tells the host, this is the neighborhood we live in.
And the host then takes that prefix, generates its own interface ID using EUI64 or another method, combines the two halves, and boom, it's online.
Exactly. No central server state is required for basic connectivity. It's incredibly robust.
But wait a minute, we have a problem, a big one. If I'm using EUI64 to generate my interface ID, we just established that my interface ID contains my unique hardware MSA address.
Yes, that's correct.
My MAC address is permanent. It travels with me. If I take my laptop from my home network to a coffee shop, and then to my office, and then to a hotel in another country, the network prefix changes at each location. But that last 64 bits, my interface ID, it stays exactly the same.
You've just identified the massive, glaring privacy hole in the original EUI64 design.
It's like a tracking cookie baked into my network address.
It's worse than that. If I'm an advertiser or a government agency or any kind of tracker, I can use that stable interface ID to build a detailed profile of your physical movements across the globe. I can see that the exact same device is appearing in all these different network locations over time.
That's a huge privacy nightmare. So how did they fix it? They must have fixed it.
They did, thankfully. We basically stopped using EUI64 for end-user devices. Modern operating systems, Windows, Mac OS, Android, iOS, Linux, they all use something called privacy extensions, which was defined in RFC 4941.
Privacy extensions, how does that work?
It's simple. Instead of using the predictable MAC address to build the interface ID, the operating system generates a cryptographically secure, random 64-bit number.
So it's just a random string of characters.
Exactly. And, crucially, it rotates it. It doesn't keep the same one forever.
It changes it.
Constantly. It generates what's called a temporary address. Your web browser and other applications will use this temporary address for all outgoing connections. And by default, every day, or sometimes every time you reboot, it throws that address away and generates a brand new, completely random one.
So from a tracker's perspective, I'm a constantly moving target. I'm a different person on the network every day.
Exactly. It breaks the ability to correlate your activity across different networks over time. It restores your privacy.
So with all this great automation from SLAC, does this mean DHCP is dead? Is there any need for it in an IPv6 world?
Not dead.
Yeah.
Different. Its role has changed. We now have DHCP-v6. In the enterprise world, administrators still like to have control. They might use what's called stateful DHCP-v6, which works just like the old days. A central server hands out the exact IP address and keeps a lease record of who has what.
So full control.
Full control. But there's also a really popular hybrid mode called stateless DHCP.
Hybrid. How does that work?
The host device still uses SLAC to get its IP address. So it gets the prefix from the router and generates its own interface ID. It's completely autonomous for its address.
Right.
But then it sends a message to the DHCP-v6 server to ask for other information, like the IP addresses of the DNS servers or the domain name of the network.
Ah, so it's the best of both worlds. The IP address is decentralized and robust, but the other configuration options are still managed centrally.
Exactly. It's a very common and powerful deployment model.
Okay, let's quickly circle back to multicast for a moment in segment 7. We mentioned the all routers group. There are a few of these key, well-known addresses that listeners should probably know if they're ever looking at packet captures.
Definitely. There are a few that you see constantly.
What's the most common one?
FS02.1. That is the all nodes on link address. It's the closest thing we have in IPv6 to a broadcast. When you send a packet to that address, every single IPv6 device on the local network will receive and process it.
Okay, so point one is everybody.
Right. Then you have FF02.2, which we mentioned. That's the all routers on link address. Only devices that are configured as routers will listen to this. Your laptop will ignore it.
And you mentioned DHCP has one.
Yep. FS02.1.2 is for DHCP relay agents and servers. They listen on that address for clients looking for configuration info.
And the scope of the multicast, how far it can travel, is built right into the address itself, isn't it?
It is. It's very elegant. The address always starts with FF. The third digit is some flags, usually 0, and the fourth digit is the scope ID.
So that fourth character tells you everything.
It tells you the boundary.
Yeah.
If it's a 2, like in FSO2, that means link local scope. The packet is not allowed to cross a router. It must stay on the wire.
What if it's a higher number?
If it's a 5, like FSO5, that means site local scope. It can travel through routers, but it's supposed to stay within a single company's campus or site. And if you see an E, like FF0E, that means global scope, which can theoretically be routed across the entire internet.
So it's like a set of concentric circles of shouting. You can tell exactly how far the packet is allowed to travel just by looking at the first 4 characters of its destination.
It's an extremely elegant design. It prevents multicast traffic from accidentally leaking out onto the public internet where it doesn't belong.
Okay, finally, let's get practical. Segment 8, the router. We're a network engineer. We just unboxed a brand new Cisco or Juniper router. We want to run IPv6 on our network. Does it just work out of the box?
Usually no.
Yeah.
By default, most enterprise routers act just like a computer, like a host. It can receive IPv6 packets for itself, but it won't forward them between different networks. You have to explicitly tell it to become a router.
You have to flip the switch.
You have to flip the main switch.
And that switch is what? A single command?
On a Cisco device, it's the global command IPv6 unicast routing.
IPv6 unicast routing, that's it.
That one command turns on the entire IPv6 routing engine. It tells the device, you are now a gateway. It immediately starts sending out those router advertisement messages we talked about. It starts building and processing the IPv6 routing table. It comes to life as a router.
And speaking of that routing table, how do we write the most important route of all? The default route. In IPv4, the gateway of last resort was the strange-looking 0.0.0.0.0.
Right. In IPv6, it's much more intuitive. The any network or all networks address is written as 0.0.
Okay, let's break that down. The double colon represents all zeros.
Correct. And the 0 prefix length means match 0 bits of the address.
Which means match everything.
It matches every possible address in the universe.
Yeah.
So the full command is IPv6 rep 0.0 and then the address of the next hop router.
It's the ultimate wildcard. I don't care what the address is. If you don't have a better, more specific path in your table, send it here.
Exactly. It's your exit ramp to the rest of the internet.
Wow. So, we have covered a massive amount of ground here. From the almost spiritual scale of 10 addresses, to the hexadecimal math, to the weird bit-flipping history of EUI64, the hardware-level filtering of NDP, and the automated privacy of SLAC.
It's a lot to take in.
When you step back and you look at the whole system, this isn't just an upgrade. It's a complete and total re-architecture of how the internet fundamentally functions.
It absolutely is. IPv4 was, at its heart, a research experiment that escaped the lab and took over the world. It was brilliant, but it grew organically messily. We had to patch it with NAT, we had to patch it with private addresses, we bolted on security later.
It wasn't designed for a world of 8 billion people with 5 devices each.
Not at all. IPv6 is the result of looking at 20-plus years of those mistakes and those patches and saying, okay, if we could do it all over again, knowing what we know now, how would we architect this properly?
And the answer is a system that restores the original vision of the internet.
Precisely. A global network of unique, directly addressable end-to-end peers.
So, here is the final provocative thought I want to leave our listeners with today.
Let's hear it.
We talked about the Internet of Things, and that term gets thrown around so much it's almost become meaningless. But think about the math and the architecture we just discussed.
Okay.
In our current NAT-based IPv4 world, your smart light bulb cannot have a real public address. It has to hide behind your router. It is, by definition, a second-class citizen on the network.
It can't initiate a connection from the outside world. It's firewalled by NAT.
In a native IPv6 world, that light bulb can have its own global unicast address. It can be directly addressable from anywhere on the planet securely.
That completely blurs the line between online and offline until the distinction basically disappears.
Exactly.
When every sensor in the concrete of a bridge, every stitch in a smart garment, and every solar panel on every roof has its own globally unique identity, The internet isn't something you log into anymore. It's just the environment you live in.
That is the future that is sitting on your network card right now. So a little homework for you, the listener. When this is over, open your terminal or your command prompt. Type ipconfig if you're on Windows, or ifconfig, or ipaddr on Mac or Linux. Ignore the short, familiar IPv4 address. Look for the long, scary hex string. Look for the FE80. Look for the 2001. That is the modern world. It's already there on your machine.
It's just waiting for you and the rest of the world to start using it.
Thanks for diving deep with us. We'll see you in the next epoch.
Until then,